Welcome to week 6 lecture on comparing means and groups using t-test and ANOVA. So this is part 2. We're going to focus on t-test, and part 3 or section 3 we'll look at ANOVA. So what is t-test? T-test is a way to compare the mean difference between two groups, right? So the null hypothesis when you do t-test is always saying that the two groups that you're comparing are statistically equal, or they're not different, right? While your alternative hypothesis is always trying to say that the means of these two groups are statistically different, or they're not statistically the same. So one of the key conditions or assumptions for t-test is your data has a normal distribution. The t-test is basically a ratio of the groups, like between groups and difference groups. And largely when you do this in SPSS context, the result will be calculated for you because the algorithms or the codes to calculate the t-test has been already embedded into the software, into the SPSS software. The heuristics or rule of thumb is you want a larger t-score, which means that there is a larger difference between the groups, the two groups that you're comparing. Well, smaller t-score means more similarity or lesser difference between the groups. There are at least 3 types of t-tests: one sample, independent sample t-test, and paired sample t-test. So remember, when you look at t-test, your outcome variable has to be continuous. If the outcome is categorical, then you might not want to use t-test. But if your outcome variable is continuous or metric scale, right? Continuous, metric, what else? Continuous or metric, this is most commonly used term, right? And you're basically interested in one independent variable, then you can use t-test, right? Although you will see in some instances, people are comparing multiple groups. Let's say they're comparing 3 groups, but they still use t-test. But they break down the t-test into several components. Let's say they're comparing three groups. They will compare group 1 and 2, group 2 and 3, and group 1 and 3. So, but okay, that's how they do it. So your independent variable is only one and it's categorical, which is the group, and the test is the score for that group. So that is what they are testing in the t-test. You can calculate t-test using t-test calculator if you want, like that example. So you can see that I create a dummy data there of group 1 versus group 2. I give just some number. I assume that this is a GPA of students, right? I want to see whether you know, the students who have used a particular learning method, let's say submitting their exercise and quiz every week, whether they will get a better GPA or not. I'm just playing around with this, and I enter this data because the website allow me to enter the data 3.4, 2.9, 2.6, and 3.2, 3.1, and put everything, and I enter the information and say unpaired t-test, and it will just give me the results. So you can see that the p-value is not significant, and the confidence interval is passing through a 0. 0 is between that range, so it's not significant. And you can see the t is also very small, right? So the t is calculated by that means of the group 1 minus means of the group 2 divided by overall standard variation of the 2 samples, or SE. So you can use t-test to test hypothesis. So you first state your theory and hypothesis. Of course, you collect your data as a second step. Then you can decide whether you use t-test or not, right? And then in t-test, you need to decide what type of t-test it is. And then you conduct the t-test, you look at the descriptive statistics, check for this test of equality of variance. One of them is called Levine's. I think this is a person's name who invented this method, and check the F, and then you check the p-value. I'm sorry, there should be no. And the p-value is the key part here to determine, you know, your t-test, and you make a decision. So one of the type of this is called one sample t-test. So one sample test is the simplest one, in which you're comparing your t-score against a test value. So how does it work? How does it work is, for example, from the literature or from a trusted organization or from legal requirements or some industry standards, there's a certain value that is considered ideal or considered very important. And you want to see whether the sample of the organizations of the people that you are studying is very different from that test value or ideal value. Just one example, the government say there's a certain standard of a particular chemical that homes should not exceed, right? And then you go to people's homes, like, I don't know, hundreds of them. You collect the chemical samples and you calculate the t-test, one sample t-test to compare against that 10 micrograms as the test value. Or if you want to know whether the GPA of the high school students in CTX, that is, CTX has 200 schools, you take the GPA of randomly of these students, right? And you compare that with the national mean value of the GPA of all high school students in the country. And you want to see whether the GPA of these students in this CTX is much better or much lower, or very different from the population average, which is the country level average. So in sample test, in one sample test, basically you're comparing the groups that you are interested in with the population that you are testing. So this is an example. You can use the Salary.sav file to try this on. I try this to answer this question. Do the current salary of people in the banking industry earn more or higher than the known population of average of $12,000, right? So you open that file, you go to procedure, analyze, compare means, one sample t-test, and enter that test value of 12,000. So that is how you do it. You enter the current salary, and in the test value, that's the most important part. The test value is the test that you are testing against. Enter 12,000, and I click the result, and it will give me this output. I've got a mean value of 13,000. So the salary of the sample of the people in that survey.sav file, they're all bankers, the people who work in the banking industry. The mean value of their salary is 13,000 something, 13,700 something, right? And then the test value is 12,000. So you can see the mean value is that. And look at the mean difference. The mean difference is 1,700 and is significant at p less than 0.001. And you can also see that the test value is 12,000. So you can see that the p value is significant. So there's a significant difference between the bankers who are in a sample of your survey. They're significantly different from the test value of $12,000, right? And you can write a quick conclusion of this one sample t-test to say you have collected data from 100 employees, and the mean of this group is how much, which is greater than the population at what p level, and the t at the degrees of freedom 473 come from that one. The degrees of freedom after the t, there's a df 473. That's where it come from. D473 at 5.63. So the t-test is 5.63. Right? Look at the second table in the middle there. T 5.63. So that's how you write out, and it supported the hypothesis that people working in the banking industry earn higher income than the national average. So that's one example. In independent sample t-test, or what we call between subjects t-test, is where you are testing people who are not related, and people who are not doing the same tasks or the same experiment 2 times. You just want to see whether people are different or not, right? And again, in t-test, your grouping, or the independent variable, is categorical, while your dependent variable is continuous, right? Like, for example, whether male and female, which is gender, categorical, have differences in their salary. Salary is measured as a dependent variable, and it's continuous, right? So you can use t-test for this. So this is an example where the research question is whether female workers have lower income than male workers. Again, I test this on the Salary.sav data file, and you just go to analyze, compare means, independent sample t-test, enter the test variable, and do the groupings, define the groups. So in an independent sample t-test, you're trying to compare 2 groups and to see whether the 2 groups are different or not statistically. So using that Salary.sav file, if you follow the procedures that I mentioned to you early on, right? And you enter the test variable beginning salary, and the grouping is 1 and 2. You need to pay attention to your data file. In the data file, the coding, the data file in .sav file, the coding for male was 0 and female was 1, right? So, and then when you define the groups here, when you click the define groups in the box, it will ask you to assign which one, group 1 is equal to what, group 2 is equal to what. So you need to be consistent. You cannot be reverse it, because you're going to get very confusing results. So because male was 0 and female was 1 in the data file in .sav file, so when I'm entering this information on defined groups, I define it as group 1 is male, male is 0, so group 1 is 0, group 2 is female. For me, group 2 is female, and the female is 1, so I enter 1. So I click continue, and it will give me the results. So the result shows here that the mean salary for the beginning salary for male is 8,100 something, and standard deviation is 3,600 something, and for the female is 5,200 something, and standard deviation is 1,000 something. So you can see clearly that on average, just from the mean value, men earn higher salary or are offered higher salary than women. However, look at the standard deviation. That's more interesting. The standard deviation shows men also vary a lot in their salary. So some men will be earning a lot higher and some men are earning a lot lower. But for the women in this sample, the standard deviation is much smaller than the men, right? It's only almost 1/3 of it, right? So 1,000 something compared to 3,600 something. So which means that women are more or less more consistent, but lower. More consistent in terms of standard deviation, but lower in terms of mean compared to the men. And then you need to look at the Levene's test of equality of variances. Remember the assumption here for t-test, the rule of thumb is you want your homogeneity of equal variance to be not significant. You want the p-value to be greater than 0.05 so that you can claim there's a difference. So that is the assumption that you need to have. Because the result is significant there, you have a significance at less than 0.001, right? Then you take the other one. You take the other one, which is the one at the bottom. Equal variance is not assumed, right? You look at the t-value and the degrees of freedom and the p-value at two-sided and the mean difference. And you can quickly write your results. You can say you collected data from how many people. The mean value of male is 8,000 something, which is greater than mean salary of the female at a certain number and significant at the t at what is 318 is degrees of freedom. You can see there at the bottom there at t 318 at the t value is 11.98 something, and which supported the hypothesis that male earns more than female for the beginning salary. So that's just how you do it. The next one is called repeated measures t-test, or what we call within subjects. So you do repeated measures of within subjects because you are testing on the same person twice, right? You call it also pre-test, post-test design, or before-after t-test, before-after test. This is another name for that. So don't worry about the meaning. As long as the same person participate in the experiment 2 times, then this is called repeated measure or within subject or pre-test, post-test, or before-after is the same. Okay. For example, you have a new teaching method, right? You want to know whether this new teaching method will improve student grades or not. So this kind of question is very suitable to use repeated measure, right? Because you will use the same student, and some of them use the same student, and you give them the intervention, which is the new teaching method, and you measure their dependent variable. So I've created a data file called pre and post test in an Excel file. You follow that, analyze, compare, pair sample t-test, and you enter the variable called pre and post test and paste it and get the results. So in pair sample t-test, you want to see whether there's a difference in the same group at 2 different times. So that's what I mentioned. Right? So if you have entered that analyze, compare, means pair sample t-test, you enter post test and pre-test into pair 1. So you appear on the first horizontal, and you just check for effect size and standard deviation of the difference. Then SPSS will give you the results. So this is the result. You can see the mean value for pre and post. So see the post after you have provided this new teaching method, the post-test score of the participants increases. But how significant is the increase from 79.6 to 82.4? You can see the second table, it shows the p-value is less than 0.01. So it shows that the post-test result are higher than pre-test result, which shows that your teaching intervention, your new research, your new teaching methods as an intervention has produced the desirable outcome, or it works, right? And the significance is positive and significant, right? And you can see also there's a significant difference that exists between the pre and post, right? Look at the t-value. The t-statistics is negative. I can see itself. So it's negative means that the pre-test is lower than the post-test, which support the mean value. The pre is lower than the post-test. And the t is minus 2.635, and the significance is lower than 0.05, which is 0.027. And you can make a conclusion that the repeated method t-test shows a significant difference between the pre-test, and you give the mean value and the standard deviation, and you give the post-test of what you have measured in terms of its mean value and standard deviation, give the t statistics with the degrees of freedom and the t-value with the p-value, and you make a conclusion that this shows that the interventional treatment via the new teaching method is significantly improved the post-test score, and therefore this study supports a hypothesis. So yeah, if you have only one sample, you could use a one sample t-test. If you have one sample, but basically you do it 2 times, right? You can do a paired sample t-test. But if these paired sample are independent, you use what we call independent sample t-test, right? We don't show it much here, but the most commonly used is paired sample or independent paired sample t-test, right? So independent sample t-test is the one on the most bottom right, independent sample t-test. That is the very common. The second common is the paired sample t-test, right? So if your groups are more than 2, typically you need to use ANOVA. Remember, if you have 2 groups that you are comparing, right, you can use t-tests or different kind of t-tests depending on the type of the data. If you're comparing more than 2 groups, which is 3 groups or more, then you need to use ANOVA. Remember, for ANOVA, your independent variable have to be multiple IV. So actually, a lot of ANOVA, the IV is actually the grouping. Let's say you have 3 or more than 3 groups. Let's say you're comparing people with different profession. Let's say engineering, business, healthcare, clerk, 4 different type of profession, and to say whether they differ very differently, they vary differently in terms of their salary. Salary is continuous. You have 4 different categories or multiple IVs here, so you can use ANOVA. So that's one example. So again, ANOVA is perhaps one of the most popular inferential statistics technique to determine whether the means of different groups that you're comparing are significant. Typically, you want to compare 3 or more groups, right? Now, ANOVA is also known as F-test. Remember when you did the lecture on regression, you also have an F-test, ANOVA table. So it's very similar with this one. Actually, the test is exactly the same. It's called developed by Fisher. It's a very famous statistical Fisher. So this F-test is also used to reject or support your null hypothesis, in which the null hypothesis always say the groups mean are equal or not different. While the alternative hypothesis says, which is why you want to test from your experiment, your alternative hypothesis always says that the groups are not the same, or they're statistically different to each other. Right? So typically you want your F-test to be greater than 1. Actually, the bigger the better, because it comes with a certain formula that certain part divided by certain part. And when this is greater than 1, it means that they're very different. So you still need a normally distributed data, and your samples are independent of each other. And you want a larger F statistics, which shows the larger difference among the groups that you are comparing. There are different types of ANOVA here. We are not going to cover all of them. You can have a look at books. There are certain books that, for example, by Andy Field, which is a very good introductory book on statistics that talk about all types of ANOVA. But today we're going to look at only one way ANOVA. So ANOVA is, these are kind of difficult questions. You have 3 groups that you want to compare, or 3 you can think of it as 3 interventions. So you want to test whether you have 3 levels of a medicine: 100 gram, 250 gram, 500 gram. And you want to know whether this will cure people better or not. And you randomly selected 1,500 people. That means you have 500 people in each group, right? 500 people for receiving 100 gram, another 500 people receiving 250 gram, another 500 people received 500 gram. And then you test how well is their health or their recovery from the sickness. And you collected those data and you can do this ANOVA analysis. So what ANOVA or F-test, ANOVA stands for analysis of variance. So F-test is basically comparing the between group with the within group. Within group is within that group. So let's say you have a group, you have people there. So you compare the between the group and the within the groups. So there's a certain formula, but you don't have to calculate this by hand. You can also do it by Excel if you want, but you don't have to. And it will give you the calculation. Now, how you use ANOVA is, of course, you have to have a theory or research model or an hypothesis, and then you collect your data by some experiments, or even in a survey, you can still use ANOVA, and determine whether you have a theory or not. If you have a theory, you can have a planned comparison. If you don't have a theory, you're still exploring, you can use a post-hoc comparison. And you perform your ANOVA, you check your descriptive statistics, is it normally distributed, etc. And then you look at the variances, estimated variances, and look at the F ratio, and then you make a decision whether you accept or reject. So One Way ANOVA, this is what we are looking at in for the lecture. For post-hoc comparison, you hunt for differences after the analysis. So you don't have a very strong theory to start with before the experiment. So still, we are using this Salary.sav data file. We want to know whether the type of job affect the current salary level. So type of job is categorical, but it's more than 2 types. There are many different types in that Salary.sav file. Have a look. And salary level is dependent variable and it's metric or continuous, right? So you follow the procedure: analyze, compare means, One Way ANOVA. You select your DV, your IV. You can do your post-hoc using Bonferroni, which is very popular, and click the options, particularly the descriptive and homogeneity, variance, and means plot, and you get the results. You can also use Brown and Forsyth and Welch test if you want. So this is what I did following the procedure using the Salary.sav file. Analyze, compare means, One Way ANOVA. I check for Bonferroni, and then I check for, I enter the variable current salary as the dependent variable and employment category or job cat as the short phrase of that. And I estimate the effect size, click OK. I check for Bonferroni. I want descriptive and homogeneity variance tests and with means plot. And that will give me this result. And this result shows that among the different groups of professions and in terms of the salary, and I look at the top one based on mean, right? Significant, which shows that actually for the Levine's test, Levine's statistic, you want it to be not significant. You want it to be not significant so that the equality of variance assumption is met. Okay, so this may be counter to what you have learned about p-value. So in Levine's test, you want it to be not significant. Right? So this shows here the result from the Salary.sav file among the different types of profession and people's salary. It shows that p-value is significant, which means that the assumption of homogeneity of variance is violated. So when it's violated, what can you do? You can still go ahead with the comparing the groups, but just have to be very careful and caution. It's never really causing a problem, but you just have to be careful. So this is descriptive of how the different types of jobs have different salary level, and look at the mean and the standard deviation from clerical, office trainee to technical. And there's also a means plot that I've ticked earlier, and this is the means plot. You can see that the salary there. Look at the technical is different, and the clerical is low, and office trainee is low. But the key part is look at this ANOVA table. It shows that the F is very high, it's much greater than 1. And it's significant. So this shows that from the F test, the p-value is significant, which suggests that the different types of job and their mean value is very different in terms of the mean value in terms of the current salary. And it shows that certain type of job are much higher than other job. Like for example, the technical is much higher. Technical has a salary of 36,691, while clerical is only 11,000 something. And then because you're doing the post-hoc, you don't have a theory, you're doing a post-hoc, you can hunt for the differences. Where is the, so this is a treasure hunt. You look at where is the actual differences. So I compare, look at I highlighted in blue or in, I compare the differences. And I will say, oh, course training and clerical, what is the difference? So you can see the sign positive, negative, right? So remember, mean difference is I minus J. I minus J. So for example, the top one, clerical is I, and the J is office training. So that's clerical minus office training. So it's minus, it means clerical is lower than office training. So it's a minus 1,592. So you follow the same procedures to interpret the findings. So then you write the conclusion. So you can say, for example, in summary, we've collected data from how many people, and there's a statistically significant difference in the type of job and the salary level at F at two types of degrees of freedom, 6 and 467, and the F statistic value is 171, is significant as less than 0.05. That is the technical officers, MBA training, ex-employees, and which trains are significantly different in salary level. But we also find that the clerical office training security level are not significantly different in salary level, and so are the college level. So you can tell in more detail after you have done this part. After you've done this part, you can tell a more precise story in terms of your conclusion. And the other one is called One Way ANOVA with planned comparison. So this is where you have a theory to test your hypothesis, right? For example, there's a certain theory from literature that say people who have technical job are important in people who have a technical skills or in a technical job are likely to hold more important contribution to the company's success, right? And they say they tend to be paid more. So that is your hypothesis that based on literature, and you want to test it in your study. You have done your study, you collected your data, and you want to hunt for these differences, right? So you can look at, so you have a hypothesis that technical jobs are likely to be possibly associated with higher salary, right? So technical job is just type of job. So they're categorical. There are more than 3 types. That's why you can use ANOVA. If it's just 2 types, you can use t-test, right? But there are more than 3 types here. And the DV is salary, which is metric or continuous scale. And then you go to use the salary.sav file, go to procedure, and you enter the analyze, compare means, one way ANOVA. You do the contrast efficient, you give the technical category as, so the total number has to be 0. So because you have 7 types of job here, and technical is the last one, right? So you follow that rank. Sorry, that's the structure of the different type of job. You can go back to the previous slide in the table, right? From clerical, office training, blah, 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 until technical. So you put the other is minus one, and then you put the last one technical as 6, so that when you add it up, they become 0, right? And then let's go to planned comparison. So again, just to show you, you go to analyze, compare means, one way ANOVA, enter current salary as your dependent variable, enter the employment categories, job category as your factor or your grouping factor, or you can call it your independent variable, the same. And you need to contrast, click the contrast button there at the top, and you enter -1, -1, and the last one is 6. 6 is for the technical job. And once you enter it, it will give you the result. So this is the key part called the Levene's homogeneity of variance test. Again, as I mentioned earlier, that the assumption for Levene's homogeneity of variance, that you want it to be not significant. But here again, it's significant, right? The mean difference of these people are different type of person compared to the technical job is statistically significant. So this shows that the p-value is significant. That means that the assumption of the homogeneity of the variance is violated. So because it's valid, then you can still proceed, but you have to be cautious with the interpretation of the results. And this is the output again, with the degrees of freedom of 6 and 467. You have a F statistics or F score of 171.1 as significant. So you can make a conclusion that from the ANOVA table, the p-value is significant, which means that the technical job is significantly associated with higher salary. And if you look at the means plot, it's true that the technical job is higher than anyone else. And you also look at contrast coefficient that just to tell you like where you did the coding. Unfortunately, SPSS doesn't give you the more precise, so you can only see it at the detail at the output. Preferably, if you could do the further reiteration or refinement of SPSS, hopefully SPSS will allow us to check what the code that we put, which one is for which one. For example, when we enter that contrast coefficient, we don't know who is number one, who is -1, who is the second -1, who is the third -1. But here you can see the contrast coefficients, right? Because it's significant, remember the previous test, the Levin test is statistically significant, then you go for this, you choose the does not assume equal variances, and that is how you report it. So for example, you say the results show that technical job is positively associated with high salary and is significant at 0.008 or lesser than 0.005, and this supports that the technical jobs are likely to be positively associated with a higher salary. That's it. So in conclusion, experiments is wonderful, it's amazing. It can help us make better decisions, to test interventions, programs, policies, strategies, to know which one work better than the alternatives, right? And experiment is the only approach or the only method to allow us to show causality. And it's called the holy grail of the social sciences. Not everyone agrees, but in general, people agree that experiment is very powerful. But there are some trade-off in the experiment. You want it to be real, or you want it to be simple, or you want to get more insight. So one is very real, yeah, but it's too complicated. Your insights might be lower. But when it's simpler, not as rich as the real, you get deeper insights, but it's also not easily transferable or generalizable to other places, to other contexts. So you have different trade-offs here. So you need to find the right methods to use. And the second part is the different type of analysis. So you need to know when you want to use t-test, when you want to use ANOVA. So ANOVA is great when you want to compare two groups in which your IV is only one and it's categorical, right? For example, comparing male versus female on their salary. Salary is continuous. The DV is a continuous variable, right? Or you're comparing whether medicine A versus medicine B, which one works better in curing diseases. So you have only one variable, the medicine, and your dependent variable is how well it cures people, right? So ANOVA use it for 3 groups or more, and then your groups or your grouping or your independent variables are categorical, like different type of jobs or different religion, 5, 6, 8 different religions, or people in different education groups, and a continuous scale as your DV. We haven't covered the others like MANOVA, MANCOVA, randomized control trial, choice experiment, and survey experiment, which could be done in the future. But we'll stop it there. Actually, in the following week, we will have guest speaker on conjoint/choice experiment. I end it up here, and hopefully that's useful for you. Thank you. Bye-bye.